beginning to worry I was in the wrong meeting.
Yeah, I'm driving home, so I don't have video. I thought I'm a little bit late, but guess not.
Oh, Rob is on the other side. We can see his face now.
Yeah, I was not feeling great this morning, so I decided to do everything via Zoom today.
Sure. So we get an opportunity to see your face. Yeah, actually, yes, we see you even at least a couple of times in the department seminar, I think.
So I can say I'm the only person who is attending the classes in person all the time.
So you have never missed it.
Well, it was the first day, but I was here. And
Oh,
they
you were kicked out by
Yes, I was
others.
kicked out, yes.
Yeah.
That I say I was here.
Yes, I think you should get that.
You're still wearing a mask on Zoom. If I remember correctly.
So you forgot.
No, I was not.
So people have not seen your face. That's the point. Yeah,
Oh.
go ahead. Jordan, yes. Oh, Jordan, you're here. How is? Yeah, go ahead.
My connection may die at some point because I'm driving home from the hospital, so it may or may not last, depending on where I'm at. I'm gonna try to be here
How do you take notes, Jordan?
What's that?
How do you take notes while you're driving?
Well, I can't take notes while I'm driving, but I can listen and then take notes. I rewatch all the lectures
Okay.
and take notes that way. I've began doing that anyways. It's beneficial to me.
That makes more sense.
Just to answer your question, because I think you asked how things are going.
Yeah.
She got put on a ventilator Friday evening, and then this morning they were able to take her off the ventilator. So we decided, we should come home or whatever. But yeah, on Friday evening we went back to be with her family. So we were, she's 86, so it's regardless, she's expected to make it through, but she wasn't in the best shape, prior to having it either. So that's just you never know. So we're being cautious and trying to be there when we can. And
Sure, do what you can. I think that's what.
She lives in a home. Kind of what makes it difficult is she lives in a home with a bunch of other elderly people. So over the past 6 months, nobody can actually go there and visit her, or because of COVID, nobody's allowed to go there or leave there. So they have to kind of lock it down. So nobody in the family's really seen her besides talking to her on the phone in about 6 months. So hopefully she makes it through this, and then the COVID stuff dies down at some point. Everybody will get to see her and talk to her. But
Yeah, that should be priority. Don't worry about the course. So do whatever you can, catch up later. So don't worry about late submissions or anything.
I think I should be kind of back on track tomorrow. I think I talked to my wife and told her, if anything else happens, I have obligations that I still have to fulfill. So I'm going to try my best to return back to normal tomorrow. Hopefully.
Yeah, I'll leave that decision to you. Yeah.
All right.
Yeah. Oh, Alia.
Hello.
Okay, Rob, you had something to say before we begin, correct?
Well, because I wasn't on the road this morning, I think that one of my questions was dealing with with the Heaviside step function and the integral, because the same things that we were able to do with the delta functions didn't quite apply to it. But I think I overcame that part. As in, I've got something that if I were to take it to the limits of limiting it to the z-axis, it works. And I think after that, you know, obviously, I think there may be a little confusion on the idea of if we are to find a value for something in a very restricted sense, like along one axis, that can be, I guess, wrapping your brain around how that can be expanded for all cases.
Okay, good point. What about, so yeah, I hear you. So what about others? How did the problem, is it problem 3, last problem in the midterm go? Have you guys finished it?
I was able to finish it using a delta and a step function.
Would you like me to do that today here in class? Do you think it will help since you guys have spent some time, or should we proceed? And so there are two options. I can spend 5-10 minutes on that and give you some hints on it, which will be pretty much the same as what I did for the ring, which might not be like, it might be good for you guys to see one problem completely. So I don't mind doing the whole disk since you guys have spent sufficient time now, hopefully. Sometimes when you are prepared, it helps you more when I give you some small details in there. So I can work out the whole problem here in class if you guys want. It'll come at a price in the sense we'll miss something in the course, but that is always like, it's like doing instead of 5 examples, I'll do 4 examples. So it's not that you will miss too significant thing. Do you guys want me to do that? Any votes, any specific? Anyone thinks no, we should keep going?
Should the answer be with something and then with a delta z? Like
no, because the potential will be everywhere, right? So probably not delta z, no. Potential. So if you say the answer has potential has a delta function in it, that means for z not equal to 0, the potential is 0, which is not the case in this case. So no, I would say no.
Okay.
Yeah. So yeah, so since there is not any strong opinion there, so let me say that I will do the problem. Okay, and we'll see how it goes. Yeah, I have never done this completely to the end, I should say. I have roughly sketched it out on my. So I might be missing things too if someone sees any problem. But I did notice that you pretty much mostly completed it. So
yeah, Moses, Rob, and I worked on it.
Okay.
And I think we mostly got the logic, but I had trouble with like writing the form of the expansion.
So when Rob says he had some concerns, he represents both of you together. Okay, good. So then it is already three of us. Yeah, Rob does say in his email that I represent some of us, but he doesn't specify who it is. So I don't know who all is in the he's in the revolution. Who are all in the revolution committee? I'm not sure. so yeah, no, this is good. Okay.
You're doing a good job, Rob.
It's always respectful.
I'm asking the identity of your fellow members. That's a good thing.
So, okay, good. I think let's think so. I will have to do some change of plans here, right? Maybe so, because if I don't teach the regular stuff, oh, I have to change the camera. So there was a homework that was due on October 30th, which was a Friday. So we're going to change that. And I'll say this is what's the next? So November 6th, I guess. Right. Oh, no,
November 2nd is Monday?
Yeah, yeah, on the second Monday. I wanted Monday. I started doing the 1 week thing. And so this was a change, right?
Nothing with changed it to
It seems
16.
off. This is not, what did we say?
I think we
We
changed it
said
to
we wanted
16.
it on Monday, right? Because Rob is there. I think I have it written wrong here.
Yeah, Monday.
It was the 16th.
16th of Monday. Thank you. And in class or not, it doesn't have too much value now, I guess. Yeah, so this is a disk. Uniformly charged disk, right? I think that's understood. Let's see. For uniformly charged. How do you say this? We can go by the standard method that we say we put a charge density there, right? But then we'll get stuck, right? Because we cannot do the integral, but that's where the point comes. Okay. So that's the z-axis. We choose this to be the z-axis. I think that's doesn't lose any generality there. That's your radius r, observation point, and the source points are on the disk, and the charge density itself, what is it? So it is delta z for sure, z prime, let's say, delta z prime, and
The function rho prime minus a.
start it again.
Step function.
Step function rho prime minus a, that's correct. Yeah. Yes,
I think I
cylinder.
had
We did A minus.
R prime.
A minus rho prime. Doesn't
Okay, so I did it in spherical coordinates.
matter. It would be easier if you use a cylindrical because that disk has cylindrical symmetry.
It'll come out the same. It's just.
It should come out the same.
In spherical, we would use delta pi. by
It should simplify something else.
C2 is, so what did you, that's I think delta, correct? But then you still want,
No, that was my, so theta prime equals.
no z, right?
Yeah.
No z, because you want spherical coordinates. So this
So,
is
yeah, delta of theta prime minus pi over 2
theta prime minus pi over 2.
over r prime for the scale factor.
Yeah, but that will come in here. I think so. Or maybe not.
Yeah, we had trouble when we,
Yeah, you good point. Let's leave it alone. Let's cover that.
okay.
I think maybe that's it. I know that there is usually a Scale factor, yes. In principle, there should be a scale factor. Okay, let's do that. So that's correct.
And
R
then
prime.
same step function.
Same step function. Okay.
No, it should not be rho prime.
Except
right?
R prime. Yes.
So
This-
I mean, it is not making a difference, but the scale factor, 1 over r prime, is it with theta, that step function, or is it with
It is
delta
with
function?
theta.
Okay.
Theta. And when we integrate this, the idea is that this one of them should cancel out. So it's good to keep that. Usually delta function has, so it's good to keep that. But I would also, my first instinct is that it should be caught by this anyway, but maybe not. Right?
Yeah. So one thing about cylindrical versus spherical is I was under the impression that we had to use spherical because, or at least I wanted to expand it in the Legendre polynomials.
That's correct.
So I wasn't sure how, like, I thought that in a cylindrical realm, you would want to use a different special function.
That's actually correct. We have to use this. Yeah, I think you have a good point. Yeah, because we want to expand that 1 over square root out in the Legendre polynomials. Yes. So and that is with respect to theta prime. So that's necessary actually. So it is necessary to do that. Yeah. So I was just beginning. So I would have got stuck in the next step. So good point. Yeah. So that's necessary. If we do this integral, so if the comment was clear for others, this is necessary. Necessary, let's say, because Legendre polynomials are in terms of theta prime. Correct. So that will be, I would think that there's absolutely nothing wrong in that, but it may not help you much. You reach there will be a z prime dependence, rho prime dependence. You won't be able to do much with that. Okay, so if we integrate this, let me do this here. So charge Q, total charge on the disk is Q, let's say. That's 0 to A, right? 0 to A, R. I think usually you say this is dr prime, 0 to pi by 0 to pi, actually. R prime d theta prime, and there is no phi prime, I suppose, right? So that's 2 pi. No, there is one more R prime there, sine theta. So R prime sine theta prime d phi prime, 0 to 2 pi of this quantity, C2. Delta of theta prime minus pi by 2, and theta of A minus R prime, and I want to see what happens if I don't put that R prime. Okay, so most probably, so I'm saying this is C2 prime. Okay. This is not the C2. Just curious what happens. So this is 2 pi is there, and theta prime gets replaced with pi by 2. So sine of pi by 2 is 1. So this is 0 to A prime. So there's 2 R primes, and what? Sine theta prime gets gone, right? That's it. And C2 prime. I see. Yeah, like even the dimensions are off, right? So in principle, this could have a functional dependence on R prime. And we don't know what this could be. Yeah, so this, you get stuck here. So this is ambiguous at this point. You cannot proceed at this point because this could have an R, or we see that there is an R prime dependent. In general, it could have the scale factor. So that emphasizes that the scale factor is important. Yeah, good point. Okay, so abandon that. So go back to C2, right? So hopefully I didn't confuse you guys here. So now you come back here, and this is equal to, again, do the same thing, but this time that is C2 over R prime. So this is 0 to A, the R prime. R prime cancels out, d theta goes away, 2 pi, and there is an R prime there, and there is 2 pi. That's it. Right? Yes, and that's the C2. Yeah. Yeah, if it was a delta function, this would have caught this R prime somehow, but it isn't here. Yeah, good point. Yeah, okay. Yeah, so that's equal to pi a square, I guess, because there's a 2 factor of 2 after integration that cancels out. So it's pi a square C2. That implies that C2 is equal to Q over pi a square. Good. So we can say that C2 is Q over pi a square. Okay, and that R prime is also that. Is that dimensionally correct, I think? Really? Yeah, dimensionally correct, right? Because a square area and 1 over times volume. Okay, good. Okay, so that's your charge density. Electric potential is R theta phi is equal to 1 over 4 pi epsilon. You can proceed in the standard way. So this is, let me first write down the general expression. So this is dq R prime, rho of R prime divided by R minus R prime. So that's equal to 1 over 4 pi epsilon naught. Bring out the q over pi a square, 0 to infinity R prime square d R prime 0 to pi. Again, R prime should come with the theta primes and all, but I think it's okay. Let me be consistent about that. R prime sine R prime theta shouldn't affect 0 to 2 pi d phi prime R prime sine theta prime. Okay, and you have delta function of theta prime minus pi by 2, step function of a minus R prime. That is R prime there. So that's right away useful to cancel this. And the distance between them, which is given as R square plus R prime square minus of 2R prime, and I think I'll put that, what is this? So let me, as of now, just say this is cosine theta prime, that's your theta there, theta prime, let's see how it comes out, and plus sine theta prime cosine phi minus phi prime. And all this is proceeding this way. It's not really necessary to go until there. Probably you guys realize that we could have directly started with something, but let's proceed because that's what I keep proposing. Okay, so our prime cancels out, and theta prime is pi by 2. Cosine theta prime is pi by 2, so this goes to 0. That goes to 0. That goes to 1, and that is a cosine phi minus phi prime still remaining, correct? So yeah, 1 over q over pi a square. There is only one r prime, so this is 0 to a r prime, and 0 to 2 pi d phi prime. Sine theta prime goes away, and whatever is left out is the power. So it's r square plus r prime square. R prime now has to be on this disk. Yeah, that's where the cylindrical thing might show up, but it's not necessary. So this is 2 r prime. Theta prime goes away, sine theta, and cosine of phi minus phi prime. Okay. And you might be able to go one more step, probably, I'm not sure, with the cosine integral here, but that also probably involves legendary elliptic integral, or actually no, contour integral might get you this cosine. But we don't even proceed there. We say that, oh, we cannot proceed too much, or best is to rewrite it as a, or you just say that this is legendary polynomials at this stage, right? We expand this in legendary polynomials. But I could have done that right at this point here. Right? I didn't have to go here, but this is how you learn that, oh, I don't know how to proceed, so I get stuck here. So I go back and say that, oh, I want to use symmetry principle. Symmetry tells me that the function electric potential is a function of r and theta alone. Right? There is no phi dependence in there. And once I have this angle theta, any function in angle theta can be expanded in terms of legendary polynomials. So I call that L equal to 0 to infinity. So AL, but now this, let me leave that a little room there. So PL cosine of theta prime. Notice that this is not a step following this. I can write that also. I can write this. This is also a function of sine theta. I can say that's an expansion in PL. But go back right here. This is a function of r theta, and you expand it. If there are two parameters involved, and you're expanding in theta now, not theta prime, right? Expanding in theta, then the coefficients has to have r in it. Where else r can go, right? That's is that very clear? This is the first step. You can forget everything, including the charge density. You can forget, right? Is that?
I have one question. So when we say symmetry, is it azimuthal symmetry?
Yes, this will be azimuthal, right? There is no phi dependence in the rotation. Like that is again, what can it depend on? Right? If I move around, that is not the case when you have Green's functions and all. Like if it's a kernel we are talking about, but this is one variable quantity, right? In this case, it cannot depend on anything else because in your context, Avinash, somewhere else you might see that this cannot be done. But, okay, any questions at that stage? Okay, so Rob, this, because I have to connect with one of the questions Rob raised is that you have a function given only at one line, how are we able to expand that above that line? So it's a good question. Okay, so that's what it is. And how do we go about? So we do one more thing before we proceed, and we want to learn a little more about AL. I did this to a certain extent for the ring, but I did not do a complete job on that. So let me go back and remember here, I think I'll go to the other book. Okay, so we are proposing that our potential has this form. AL R times PL cosine theta. And it also has to satisfy the Laplacian. Is in general equal to rho, it is equal to charge density over epsilon naught, right? But it is equal to 0 if rho is equal to 0. Like that's understood in the right first equation itself, but I'm specifying that wherever there is no disk, which is where we observe, right? We never want to observe on the disk anyway, so we're not interested. So for our practical purposes, it should actually be equal to 0. And that imposes something about, that tells us something about the coefficients AL. So that's equal to 0. So what's our Laplacian? That's 1 over r square d by dr, r square d by dr plus 1 over r square 1 over sine theta d by d theta sine theta d by d theta, and finally that is 1 over r square sine square theta d square d phi square. Whole thing acting on each of this, correct? So this is summation over L equal to 0 to infinity AL or PL cosine theta. That's equal to 0. You might, if you have been critical, often when you are doing partial differential equation, you begin, and there is this statement, right? What is that called? Separation by parts, I think that's what the terminology is. Separation by parts? No, is it called? No, separation of variables. Separation of variables, usually, so if you have two functions, so if there is a function f of phi of xy, and you say, oh, separation of variable tells you that a of x times b of y, right? And if you are critical, you might have wondered, why is that? One could have argued, and one can say that, oh, the Hilbert space is broken into two, and there's a good number of arguments there. But its primary source is here, right? Once you know one form of the function, like if you break it into its eigenbasis, each eigenfunction has two pieces. Like Hilbert space that this has some unit vectors, this has some unit vectors. It's only the cross of that, or what is it called, outer product of that always comes in. And the coefficients will catch that. So that's a way to look at it. But in the beginning, that could be a lot of confusion there. But that's that source there. That's a two things in here. But here it is coming naturally. We are not requiring that. That should be the case. So that should have some answers. Okay. So that's good. So notice the first term acts on AL, second term acts on theta, the second piece, and the third term has nothing to act on, so that gives you 0. So that's clear, and that's because of the symmetry again. Okay. So Then we realize that, our legendary polynomials satisfy this equation. Oops, sorry. Theta PL cosine theta is equal to minus, right? Yeah, it's minus of L times L plus 1 times PL cosine theta. That's a differential equation satisfied by the legendary polynomials. I haven't shown you that in this class, but somewhere else, hopefully you will see it, most probably in math methods course, or else I can always escape that by saying in undergraduate courses you should have seen it. So, but I might be doing it. Depends on how far we go in that. Yeah. Okay. So gives me this to be L times L plus 1. Right? So what I have now is 1 over R squared d by dr, R squared d by dr times that is what is happening. I'm bringing out the permeation right into this form. Once I act, 2 steps. Plus 1 over R squared times this is L plus L times L plus 1, right? And that's a minus sign. And Z. Oops, but now I cannot do this, right? I'll bring the L out because this L has to be inside the sum. So I have to bring the L out, summation. Sorry. Okay. But that's the same as putting the AL in. So let me put the AL in, and keep the PL out. That tells you that this is a quantity of the kind summation of some factors times PL is equal to 0. If I use the expansion of any function in terms of legendary polynomial, this tells me that these coefficients have to be 0. These are unit vectors, remember, these are imagined, pretend those to be in your abstract sense in finite dimensional vector space. So this has to be equal to 0, a differential equation. So this is d by dr, r squared d by dr times L is equal L. Oops. 1 times AL. Right? 1 over R cancels out, and I have a differential equation. And this is the primary reason why I was interested in actually doing this problem, because I wanted to emphasize this point. So now, what is the solution for this? What's the solution for this differential equation? We did point out this last time. Yeah. So notice that, okay, it's whenever you have one of the, remember in all these differential equations, if you know one solution, you're good, right? Then we can build on from there. So let's at this point just guess it. And why? Because it's a homogeneous quantity. There is an R square multiplying, there are two derivatives with R. So it seems like power functions might work. First derivative will bring it down, R square will multiply that. Again you take a derivative, so you keep the power the same, and the coefficients can be anyway, should not matter. So that's an observation you make. So let's say AL, so this is a guess. Look up, I mean, there must be more formal ways of doing that. But typically differential equation, you make a guess and then get the coefficients correct, right? So AL of R is some constant, right? Some constant, that means to say that's what I put this approximately equal to. That's R raised to N. I don't know what the power is, let me say it is R raised to N. If that is the case, I can evaluate this, the first derivative will bring out an n there. Then when I multiply this 2, this becomes n plus 1. So this is n times n plus 1 raised to r raised to n. Right? And on the right hand side, I have L times L plus 1 times r raised to n again. Right? So whatever is in front of it, these could be constants. Right? I don't have any r dependence in that. So those constant, whatever it is, will cancel out. It doesn't matter. So now it is exact in that sense, except that there's a constant in there. So, or let's say this is equal to c times constant n. So I would say this is c there, so c there, that cancels out. So under what conditions is this satisfied? Whenever n into n plus 1 is equal to L into L plus 1. And what are the solutions there?
N equals L.
N equal to L. That's correct. And
Those are 0.
and
It's like something is 0.
0. No.
And
L,
zero is zero.
N equal to L. Like L is 0, 1, 2, 3. So N equal to 0 is there anyway. Is there anything else? So that's what I wanted to mainly point out. And that's kind of relevant in the way we are doing things. It's probably just a slight non-trivial, or I wouldn't say non-trivial. I mean, it's if you think hard, you will get it. There's one more solution, and that is that n is equal to minus of L plus 1. Can you check that? Because n plus 1 will be minus L minus 1 plus 1, that's minus L. Right? N into n plus 1 is L into L plus 1. If n is equal to L, n plus 1 is equal to L plus 1. There are two solutions here. Is that clear? Okay, if there are two solutions, usually the linear combination of them are also solutions, right? Is that clear? Any confusion there? Questions? I mean, with a lot of experience, you can avoid this, you can come back and do the other part, but once you do this formally, it gives all the conditions, all the solutions in a slightly nicer way. Okay? Okay, so now there are two solutions, that means, correct? So what are the two solutions? So this implies that AL of R can be R raised to L, correct? Or it can be R raised to minus L plus 1. So this gives you that inverse power nicely. Earlier what we were doing was we were expanding it for R less than 1, and we were trying to, or last time what I said is that, oh, figure it out, you can do the same thing the other way. Here it will come out in a slightly nicer way, but you could have argued it also. A lot of experience.
This
Yes.
is familiar.
This looks familiar.
Yeah, those AL R equals R to the L, R to the minus L plus 1. I think we did something like that when we were finding the, how do I say this, the wave function of hydrogen atom.
Yes. Yes, I'm sure it is there. But that's Laguerre polynomials. I don't think you get such nice power dependence there.
I think we got same
Wait,
power as that.
I thought they were.
Hydrogen atom is Laguerre, right?
Mhm.
So it's not power. I think, yeah, I wouldn't say you see this in. Do you?
I think I saw.
Are you sure? Because this seems.
Familiar?
Yeah.
No, I'm not saying you don't see it anywhere else, but is it hydrogen atom?
I think I saw that in hydrogen atom.
Okay, so it's okay. I'm not sure about that. Because I would think it is Laguerre. It
Because
cannot
it's
be.
spherical harmonics, right?
Yeah, it's spherical harmonics in theta and phi.
Oh,
I agree
yeah.
to that, but R is not power law. Power law are too trivial. Hydrogen atom is more than just power law. The R dependence is not, it's a Laguerre function. So I think what is happening here is that to reach the Laguerre polynomials, a differential equation, you make some substitutions. And in one of the steps, it looks something like that. But probably there is still, oh yeah, I think what it is, yeah. So if your R dependence is this, you say that I want to write this as some R raised to L, or like, yeah, R raised to M or N times G of R.
I think I remember now. So we were, I think we assumed some function and we looked at the behavior of that function. Like we looked at the asymptotic behavior and we looked at the near zero behavior.
Yes, so
Something like
probably,
that.
yes. Asymptotically, it might be G might be 1 and then it is probably, yes. That's probably what is good.
And one of those power goes to 0 and we're left with 1, something like that. I don't remember
Good.
exactly.
Yeah, usually if this goes all the way to infinity, you will say that, oh, at infinity, this cannot survive, right? It has to be this. So you'll kill this out. But when you're very close, then this will survive. Then they have to do both things, and that's what we will do now. Hopefully, let's see. Yeah, good observation. Yeah. So that's 2 of them. So it's linear combination of that, right? So let's call it AFL. Now these are constant, no R dependence, no theta dependence, and this is B of L. Notice this is subscript. So it's there's a lot of clutter with things, but since you guys have worked on this for some time, so hopefully all this is clear. Okay, so that's what it is. Now I put it back in there, right? So now remember our guess was our expansion. It's not really a guess. Our expansion in legendary polynomial had this L. So now we have sum of L equal to 0 to infinity, and you have 2 pieces now, right? AL R raised to L plus B of L times, it's good to write this as R raised to L plus 1 because it's in the L is positive, L is 0 to infinity, and this is PL, the sine of theta. One thing is very clear for large R. Let me also do one more thing here, right? At this point, yeah. So yeah, at this point, so this is the best we can go until here, right? Now so our goal reduces to finding AL and BL. Okay, that's our goal. For that purpose, we say that can I calculate something? And it is on the z-axis, right? So this is R equal to Z. R is equal to Z. R and theta, right? Theta equal to 0, you said. Isn't that what you said? R and theta equal to 0. What if I know this? Can I do something out? Because remember, our goal is to find AL and BL. If I know AL and BL, my answer is solved. Solution is done because my goal is to expand it in terms of legendary polynomials. Yes.
I was just going to say, if we say R and theta is equal to 0, that is in z-axis, right?
That is?
In z-axis?
Yes, this means it is on the z-axis. Right? This automatically is now on z-axis. Okay. Again, I repeat, so this is kind of coming to the question Rob asked as to how can I find this function just from one line? But notice, I have to find AL and DL. That is all I have, and those are constants. If I can find AL and DL, what else could it be? That it's unique, correct? At any one point, if this is independent of R and theta, if I find it for one R and theta, I'm good, right? So that's our going to be our goal. For that purpose, I calculate this, but I know the solution independently, correct? And what is the solution? Can I use that, or should I be doing that here along the axis? Is that familiar to you guys, or should I be doing that, or was there a confusion on that? Be honest.
We solved it.
Yeah, we saw.
Right. So that's a problem to find it on the axis, and yeah, can you guys help me with that if you have it?
So it's the constant, which is Q over, I guess, it ends up with the factor, is a Q over 2 pi a squared epsilon naught. Okay, so that's fine.
Yeah,
You can just do
2Q over a squared.
2Q over a squared.
Yeah.
Is this there? I'm still keeping this one.
Yes. Yeah. So with the 1 over 4 pi epsilon naught, it's 2Q over a squared.
Sure.
Yeah.
Are you sure about that?
Yeah. Because that's the same as what you said of Q over 2 pi.
So this is generally, it would be 2 pi times Q over pi a squared.
Yeah.
Right? That's your sigma. Sigma over 2 epsilon, right?
Yes.
Yeah.
So it ends
I
up
think
with,
this is this.
so it ends up, yeah, so it ends
Oh,
up,
yeah, so that is a 2. Okay, I'm not doing calculating my head. Yeah, this is the pi cancels out. Yeah, yeah. So that is a 2. Okay. Got it.
Yep.
And
then R,
8.
okay, well, you're putting, okay, so the square root of R squared plus A squared minus R.
What?
Yeah. Yeah.
Well, you already took the A's.
Yeah.
Yeah, no, that's,
R squared plus A squared. Or, yeah.
yeah, that's right.
Yeah.
That's right, yeah.
Is that completely right? Yeah, that's correct, right? Remember that, just remember the fact that R is greater than 0. That's crucial. That often this is written in terms of Z, then you have to make sure that that's magnitude of Z. So up, above the plate and below the plate, it's symmetric. Otherwise, that doesn't come out. Correct. So we make sure if this is Z, you write this as magnitude of Z. So that's the only thing that can be confusing in that. And you expand this as a function of L, I guess, correct? Yeah. Yes. Okay. So we compare. First, let me do this expansion. Another expansion. Okay, I will do it. Okay.
This is where I got stuck. So, just one question is like, do you have to do 2 different expansions?
Yes,
Okay.
yes, exactly. Because that's where this will go with one to the other. That's exactly. So there are 2 expansions. So first let me, so if I pull out an A, right, this is 1 plus R over A the whole square minus R over A. So this is the case when R is less than A. Right.
I have one complaint.
Yes, is it
The 1 over A is inside, so you pull out an
1 over A is an inside? Oh, so you pull out an A. Yeah, yeah. No, that's an error. That's not a complaint. It's not a complaint. That's an error. That's tough. Thank you. Yeah. Okay. Yes. So okay, good. So yeah. So this is 1 over 4 pi epsilon. So this is good. So okay. So the other one is 2q over A squared. This time I pull out an R, right? I pull out an R. I think it's upstairs. So this is 1 over A over R squared minus 1. And this is for a less than r. Right, that's your two expansions. And 1 over x squared, let's do that separately. I usually just expand and take it, I don't remember this. So this is 1 plus 1 by 2 times x squared is, right? Plus by 2 over 1 factorial. So this is 1 by 2 times 1 by 2 minus 1 over 2 factorial times x raised to 4. Right, plus 1 by 2 times 1 by 2 minus 1 times 1 by 2 minus 2 times 3 factorial over x raised to 6. I kind of catch the pattern from here. So I think I will keep, because this begins from here, right? 1 by 2. Can I see the pattern immediately? Yeah, I think so. Yeah. So this is 1 summation of n going from 0 to infinity, x raised to 2n, and factorial, right? Let's cut, it's coming in, and what? So this is 3, so this is n minus 2, 2, 2, 3. So that is 1 over 2 raised to n, right? And then there is 1 minus 1 times 1 minus 2 times 1 minus 2 times 2 times 1 minus 2 times n minus 1. I think so. And which I will say is raised to 2n and factorial 1 over 2 raised to n. This is 2n factorial. But then I have to multiply that. So this is minus. Yeah, this is correct. Something is wrong here, right? Oh, because there is a minus 1 I have to pull out. If this is 4 minus 1, 3, 2 minus 1, 1. So there's a minus 1 raised to how many? N minus 1 is 2, 1. So n minus 1 of them. And then I provide 2 raised to n in each, and that's 2 raised to n in the denominator. And then n factor. Okay, I did most of it in my head, but you guys figure that out. And in principle, you can just use that identity for the summation. Did I get that correct? I think it looks okay. Any confusion, questions? Please ask. Or most important, if I'm making a mistake. Minus 1 raised to n minus 1 over n factorial square. I think this is how you would write it. 2 raised to 2n times x raised to. Okay. I think I can figure all this. So what? So I say for r less than a, let's do a less than r. Outside 95. A less than r, phi of r 0, theta equal to 0, right? So r 0 is equal to 1/4 epsilon naught 2q over a square of over this whole sum minus r of 1. So this is L going from, no, n going from 0 to infinity, minus 1 raised to n minus 1 over n factorial square to n factorial 2 raised to n times x now is a over r raised to L minus 1. No, not L. Much is and we also know that, so this is one way of writing it, but we also have from pi of, like, substitute theta equal to 0 in the main expression, that's L equal to 0 to infinity, L r raised to L plus PL over r raised to L plus 1 times PL cosine theta, cosine of 0 is 1, so it's P of 1, right? And that's equal to 1. You guys with me? So now I have to just compare this, and this is a power series, and power series is unique. If you have power series for a function, it is then you can match the coefficients. Like if you have, for example, if I tell you that 3 plus 2 is equal to x plus y, that doesn't mean that x is equal to 3, y is equal to 2. But if it's a power series, so if I tell you that sine theta is equal to a L times theta L, right? Sum over L going from 0 to infinity. Here, AL is unique. If you know this, that this is a function, then AL can be determined. In fact, if you have a power series, another power series, and you're told that they are the same, that the coefficients match. Or another way of saying it is, actually, since you're talking about complete functions, x raised to L, right? The powers of L, this is actually forms a complete set, and they are unit vectors in itself. Right? That's one way of looking at it. And once you talk about the orthogonality there, that's kind of nice, but let's not do that. Okay, so I just have to compare the two. Notice in the top one, so these two are equal now, right? These two, since these are the same value, these two are equal. And we just have to ask, since n is equal to 0, there is a power of r there, right? So there is one piece that is there. We should be careful about that. But otherwise, these two are exactly the same. Right? Is that right? Yeah. So there is r here, right? When n is equal to 0, right? When n is equal to 0, this is not there, so that's r. And that will give me this a of 0, right? So, so a of L, if I'm correct, is equal to 0 if L is less than 1 or greater than 1. So that means to say, so notice L goes from 0 to infinity. This is inside the sum. So let me say this is 1, 2, 3, and so on. Because these are all in the denominator, right? All these factors are in here. There is one term from -1, that we have to figure out. Am I cutting? Oh, 2, right? Sorry. Is that right? You got it? Maybe 2.
Say again.
Maybe more, you are looking at me as if you're not satisfied. So I think it is 2, 3, 4, I guess. If 2, 3, 4, there are no powers of 2, 3, 4 in this, right? That's what I'm trying to read out. Is that correct? Check on me. Like notice that R, when n is equal to 0, that's constant, but there's an R. N equal to -1, that's a constant. No, n equal to -1, that goes to the other side. Right? Yeah.
Should the A over R be to 2n?
Oh, did I say this? Oh, that's that one. Oh, that helps. Okay. That saves me because I was wondering that usually this cross doesn't happen. Usually either we are here or there. And I'm seeing this cross, I was not happy there. Okay, very good. Yeah, okay, so that helps. Good. No, we still have this, right? Paul? Yeah, still have. Yeah, okay. So let's believe in the mathematics, right? Okay, and n is equal to 0. That's constant -1, whatever that is. Okay, but what is that by the way? When n is equal to 0. When n is equal to 0, this is 1. That's 1. That's 1. And when n is equal to 0, this is -1, correct? That is -1.
It should be 1, right?
You're saying it will be 0? Yeah, because potential should be, yeah.
Yeah.
And R, no, what am I saying? And theta on the, yeah, what are you saying?
Like when you, right when you first expanded 1 square root of 1 plus x squared, it's like 1
yeah.
plus half x squared
Yes.
minus. So
So
like
for n
the first
equal to
minus,
0, it should be 1, correct?
yeah.
So this is you're saying n plus 1, right? So I said 1, 1 minus 2. This was n.
-1 and n plus 1 is the same. right?
Yeah. Maybe just,
So it is just n, correct?
but there are 2 in a row.
2 and a
I
row.
think,
Like n equals 0 is positive, n equals 1 is positive, and then it alternates.
Oh,
Right?
oh.
Is that true?
Oh, this is correct, right? So this is, okay. This is 1 times 1 minus 2, correct? Oh, so you're saying the next one here, what is it? No. Hold on. This can be written as 1 times 2 minus 1.
Oh, okay.
1 times 2 minus 1 times 4 minus 1,
I see.
right? So
Okay.
this is
So it should be n minus 1.
right n. Right there. Because then I pull out the -1 out there, right? So we'll check the first one, how that. So suppose this is n. Okay, n is equal to 0, it surely gives me 1, right? N equal to 0 surely gives me 1. What about n equal to 1? Right, n equal to 1, this comes out. N equal to 1, 2 factorial divided by 2 raised to 2 and minus 1 raised to n equal to 1, right? 1. Yeah, it doesn't come out. That's what you were going to look at? Okay. So,
Right, but I think,
so as you're saying, we have to piece this out. 2 pieces and then, but this is a simple expansion.
yeah, I think there is a minus, like it's 1 minus a half x squared. I think that is correct. Is that?
This one is minus, you're saying?
Is it?
I think,
1 plus 1 by 2. No, this is correct. This is correct. Like I'm adding, right? This has to be greater than 1. For a very small number, this has to be greater than 1, right? If I make this x 0.000001. This cannot catch me in the first digit. So I think this is greater than 1, so this has to be plus. I think that's for sure. But okay, I'm confused here.
Can we like take 1 plus and then start, the sum starts with n equals 1 and then it starts alternating? The sign starts alternating?
Can I just look up somewhere?
I found it a lot easier to just plug in, starting with that expression, just plug in a over r as x and go ahead and work out each of the the negatives and the pluses, like just write out like the first few terms and just look at it, and then like rather than do it, make it general.
Okay, there's one more way. How about that? Since we are stuck here, these are derivatives, right? So let's call this f. Okay, since we are stuck, I'm stuck here. Okay, surely f of 0 is equal to 1, right? F of the derivative of f with respect to x, and then set x equal to 0, and multiply by 2 factorial. Is that what it is? Expansion. F of x is equal to f of 0 plus x over 1 factorial df by dx.
Yeah,
X
that's how I tried to do it, and I got bogged down with it.
So this is not going to help you think?
Only because all the odd derivatives are like go to 0,
I see.
so it's just a lot of differentiation.
I see.
But
But
it
first
can
one,
certainly help us for
checking this.
yeah.
So df by dx, so it's 1 by 2 times 1 by 1 plus x squared, 1 by 2 minus 1, so it's 1 by 2, correct?
Mhm.
And 2x, and that's 0. Oh, that's second derivative, right? But I don't want to set that, so I have to do the second derivative, right? Second derivative dx squared, that's equal to 1 over 1 plus x squared 1 by 2 minus 1 by 2 minus 1 by 2, x stays, and this becomes 1 plus x squared 3 by 2, and then there is 2x, which is equal to, I multiply by 1 plus x squared minus x squared, 1 plus x squared here, minus x squared, divided by 1 plus x squared raised to 3 by 2. That's 1 over 1 plus x squared raised to 3 by 2. Right? But you cannot get a pattern, you're saying, from this, right?
So you eventually get the pattern.
Yes.
But like that is 1, like that's 0.
This is, and it's you set t equal to 0, that's equal to 1, right? And now, and there's a 2 factorial.
Yeah.
2 factorial. So that's 2, yeah. Good. That's correct.
So now we need to take down
And
the fourth
yeah.
derivative to get the next.
Yeah.
But we only really need to consider the term when there's like 1 power of x over the denominator in an odd derivative, because that is the term that gives us like no dependence on x. Do you see what I mean? Like
Yeah. I think, tell me again.
we can probably get away with not taking the full derivative because anything with an x is going to go to 0.
That's correct. Yeah. But I need to keep that for the next one to take the next derivative, right? To get the fourth derivative, I need the third derivative.
Yeah, but you only need
Before setting x equal to 0.
right. But Yeah, my suggestion is like, if you look at the two pieces in the first line of the second derivative,
Oh,
like the second term is always gonna have an x. Right? 'Cause that
because I will do the
product is gonna keep giving you more powers of x.
more powers of x,
So you can get away with only taking the first term.
taking the first
That's
term.
what I was thinking.
Yeah. Okay, let me think again then. So if I do one more derivative of this, but what if I take one more derivative of this and in the next one, can this separate out? 3 lines down?
I don't know. That's where I gave up on that.
Yeah. Yeah, I see your point. Maybe you're right, but I'm just afraid that will I miss something?
Yeah.
Okay, but hold on. I'm also trying not to go there. I'm tempted to use this, but then what was the problem here? Right? The problem here was that this is minus 1 raised to. Yeah, we were not sure about this n, correct? That was the only problem. And I know now that when n is equal to 1, that's coming out wrong. Right? But what about n equal to 2? So let me do one more. I don't mind doing it. E cubed f over dx cubed is equal to.
I think n plus one would work, right? I know it.
It would be 0, or it'd be negative for n equals 0.
Right. Okay.
It might be right that I have to write that separately,
Yeah.
which might be okay because here also we have this separately. Maybe that helps the whole thing. But I don't remember writing a. This seems to be a straightforward expansion. But then I never actually.
Someone must have done it, right?
Yes. But then we are trying.
Yeah.
Yeah. So. Oh, it's 12:20. It's 12:20.
Yeah, I tried looking up the series and I found a couple ones that like just gave the numerical factor. So it was like 1/2, 1/8, 1/128 or something. So I just couldn't like reconstruct all the factorials and choose. Like I couldn't see the pattern from that.
Okay,
I don't know.
since I have finished, okay, let me propose something so that I can, because you guys have to submit your exam today. So I cannot leave you guys, unless you guys want to do this on Friday, like submit it on Friday. Does that help you guys? Or?
Mhm.
And yeah, here is what I can suggest. This is mostly there. I think the main part is there already. It's just a matter of comparing. And I will, yes, that much can I leave it to you guys? Or do you want me to? Because I'm struggling here. I don't feel happy about leaving it to you guys.
Yeah, this is the step where I struggled.
So, okay. So how about this? I will finish this up for you guys and but I won't make a video out of this. I will just write it on a sheet of paper and scan it and send it to you. But then you guys have to put it all together and send it back and avoid taking my own steps. At least change the words. Right. Something like that. Okay? Okay. Yeah. Yeah. So I'll proceed from here and finish it.
Would you like us to like find the series, like derive the series, or use whatever result?
I usually don't mind anyway, but I usually don't look into it. It's just a habit. I try to, as much as I can, I do it on my own. Because these are error prone. Like you look up, it's not that they make an error, you will look up in the wrong context, in the wrong place, and something might go. So it's not a good habit. For myself, I put it on that, but I don't enforce it on others. Like for example, in an exam or during the submission, you just submit it with with this series known, that's perfectly fine. In this course, that's perfectly fine.
Would you like us to submit? Would you like us to submit the entire thing Friday, or what we do the first two problems and then this problem Friday?
Entire is good. I'm fine with it. It's up to you guys. Like once I postpone it, I don't want to put any. I think you guys are working hard, so it seems to me that it's all fine. I don't have any issues. Okay. But if you guys think that no, I want to get rid of this, enough of this, I thought sufficiently, that's also perfectly fine. I wanted to get other things done, and like you guys, but you guys are all having my courses. But no, there must be other things. Come on, I mean, this is not the only thing we do.
I can not think about it until you give us your scanned copy.
Yeah. So I'll do that as soon as possible.
Okay.
But give me until today
No worries.
evening. I teach one more class, and I do a little bit for that.
And then are you extending the submission date or still submitting?
I said Friday.
Okay, Friday.
Friday, yeah.
No, this is what I wanted to say. I do have a lot of things this week, but I guess freeloaders don't have anything to say.
No, you're working hard, so that's good enough.
Be quiet, Avinash.
Well, I don't get to speak, right? Yeah, we should
You're
have a
working
sign.
hard.
Freeloaders cannot speak. They cannot have their demands met.
I think only thing you did is you didn't submit your exam thinking that you did bad. But
Oh, yeah, I thought, now it makes sense. Number two, is that A equals 1?
I think so.
I think it was too trivial. I think I was doing
Don't say
something
that.
I
wrong.
have a complaint about,
Oh, complaint, yeah. I
that's
got an
the
error.
way you graded that, I don't think that's correct.
Not square, but this is r minus r prime.
Yes, I say that right there.
Oh.
I think Moses' answer is correct.
No, but then how do you do this integral?
What do you mean?
How can you do this integral? If it is this, then you cannot do the integral.
Oh,
Right?
Okay.
That's the challenge.
so I didn't actually do the integral.
Yeah, okay, you said this here, good.
Yeah.
But then when you're doing the integral, you pretended that's r,
Oh.
Yeah,
right?
that's true.
Right.
Yeah.
That's true.
I did remember after thinking that, I wrote r minus r prime square, but by the
Yeah.
time it was
Yeah.
too late.
Okay, no, that's fine.
But this does,
Yeah, I didn't actually evaluate it, yeah.
You know what you could have done? You could have said r prime equals to 0 because it is same everywhere.
Yeah,
if
that-
Oh,
I get
yes,
r prime
that's
is equal
what
to-
I, that's what I was.
Sorry,
thinking.
not r prime. R
If you
equals
were
0.
thinking that, then you did it correct. But you didn't write it, so I cannot give you points.
Yeah, that's fine.
So at least you can be satisfied that, yeah, I was thinking correct.
Yeah,
Right. But that's exactly the point, that if you know the potential at point at the center, then you can do it. But,
right.
two of you guys did exactly what you're doing. It's not just you who did that. You tried to do the integral pretending that's an r. And in both the cases, I wrote an r prime square. Okay,
I
but
haven't picked up any tests.
it must be there in my office. If you come with me now, I'll give that to you. Yeah, Rob, I did not, to you and your disciples, I did not finish it. So,
Hey, Ross, when you agree, is it like a secret society? Can I be part of it?
yeah. So, Aliyah, is that any questions, concerns? Since
No,
I,
thank you so much, but I want to ask you something about.
yes, please.
For tomorrow, we have in math method, we have to submit the homework number 7 and 9:30 in the morning. So
I see.
since I didn't start yet because I spent all the weekend working in the exam, so that
How
is-
much do you want it postponed?
I mean, it's okay with me tomorrow midnight, but
Yeah, it's already available till midnight. I think it's due in the morning,
yes, in the morning.
but it will allow you to submit it until midnight.
No, it's not allow me.
Huh?
No, it's not. If it's in the morning, that mean I can submit it in the midnight.
No. It will allow you. What I'm trying to say is that even after the due date is over, you will have a link there. If you click on it,
It's 75.
it will allow you to submit it.
There's more alcohol.
Okay, thank you.
Okay.
That's fine.
If by any chance it doesn't work, send me an email. Okay. Don't hesitate. Just send it. Just send the file as an email.
Okay, thank you so much.
Okay. Yeah, it should work.
Ethanol, you can do
Yeah.
Thank
it.
you so much.
Okay. Here, I
Ethanol, you
think
can drink it.
I can put this on.
Yeah, this is ethanol.
Okay.
A bit stronger percentage.
Yeah, I would say they're not putting ethanol in there because, you know, usually sometimes you just, kind of rub your hand together, sometimes you just put your hand inside of your eyes, and if ethanol goes to your eyes, you're right. You don't.
Yeah.
Actually, there's one more step I wanted to teach you guys, which can avoid this to a certain extent. But
Okay.
I might do that. But does it give you a feel for legend reporting?
Yeah, it does. That series stuff is messy though.
Yeah, this one, but that's elementary, right? I think that's my mistake.
I think,
I'm being stupid there.
I think we've done this in calculus 2 class, but I just don't remember how to do it.
Say that again?
I think we've expanded that in terms of series in calculus 2 class.
Yeah, of course.
But
That's what
I just don't know how to do it
Yeah,
on
this should
spot.
be, this should be calculus somewhere. Yeah. Don't tell others that I couldn't do it.
Oh, no.
Yeah.
Well, it should
It's a
be-
discrete information. It's not gonna go anywhere.
Yeah, it's also, if you make a small error somewhere, then it's just really hard to recover.
Yeah. No, that's true. That I agree. But I think that was the reason why I was not proceeding. I couldn't guess that from there. Otherwise, usually you know what to get and you're confident. I was a little.
Also, I guess I'm a little concerned now that like this looks a lot like what we had for the charge screen, which was a 1/.
Yeah.
So
Did we have the VFBs developer of though, in that one?
no. I just mean like this expansion.
Yeah,
Looks
it's
the
yeah.
same as like the.
that,
Yeah, it is almost. the same.
actually, that might be the point that this might be the difference with charge point. Most of it is the same. It's just this that is different.
Okay.
That might be the point actually.
So it's that instead of 1/. Square root of 1 plus. Is that what it is? For this one instead of the charge string? I don't know.
Charge ring is just this first term, right? Just this first. No, it is 1/. This.
1/.
One
Yeah,
over
that's what I meant. Yeah.
And yeah, so it might be. Yeah. Let me not guess.
Right. Yeah, because I also felt like it should be easy, so that's what I was struggling with.
Yeah. Okay. Makes me feel better. 2B plus. So it's bad.
Yeah.
Okay, good. So Rob is still there. You guys want to?
I was just waiting for,
Oh, you just want me to leave so you can have your secret society meeting?
yeah, I need you to get out of here. I'm applying for tax exempt status if I've got disciples. I just wanted to make sure I caught everything since we were still talking about the problem some, but thank you.
I was joking.
You made my wife laugh.
Oh, there are people listening. I should be more careful. And I'll get in
Oh,
trouble.
no worries. Anybody that gives me a hard time, she likes.
Yeah, I never realized that you're not in a normal classroom here. Funny.
We'll see everybody later. Thank you.
Yeah,
Alrighty,
good,
see
good.
ya.
Yeah, good call, Rob. Thank you for doing this. I think this was helpful, hopefully.
Yes.
Okay. Okay, bye-bye. Yeah.